for the afternoon session. We've got a session now on non-linearities and sensitivities to policy inputs, and our first talk is from Prof.
Okay, thanks Peter. Hi folks. So this is one where I couldn't really synthesise what we'd done at the programme because we didn't do much on it. So my co-organiser said you can talk about this one because we've got nothing to say. So I've made it up basically. But there are a couple of things here that, which one of these does the thing, the light?
The one that got the pointer written on it.
Oh, the one that says pointer. Thank you. So one of the things that I wanted to talk about was emergent constraints, which Felix had raised. But I also want to talk about non-linearities and the importance of randomness in your forcing or stochasticity. And that's because, well, two things. One is that we want to constrain the range of what we're predicting, and this is what emergent constraints are about. And the other is that we probably need tipping points, which we normally think of as things to avoid, to make a transformation to sustainability, in want of a better word, like to get to lower carbon emissions, to get to carbon neutrality. So I'm going to try and argue, in a way that climate scientists like me don't normally do, that tipping points are good, and noise is good. Because it allows us to do various things like transform the system, but also detect its changing resilience. Okay, so I'm going to start with the conclusions. They'll come in one by one, so don't get excited, it's not all over yet. There is going to be a few of these. So dynamical systems, in fact, models that connect timescales, show connections between internal variability, or in fact variations in the system, and sensitivity to external forcing. And that's a really key thing. Because many of our models, I suspect, sort of take the noise out. You know, we often have, if you look at socioeconomic models, even in the climate realm, they're very smooth. And it turns out the noise is really important to test the system resilience through time. And that's basically because there's a sort of cartoon link between these things that physicists can make a little more rigorous, and it's things like the fluctuation to space theorem makes it sound fancy, but the basic idea is you can imagine a system in some kind of high dimensional well, some minimum, it's an equilibrium state, and what you really want to know is how sensitive the system might be to a forcing. And if it's in a steep sided well, it'll be rather insensitive. You'll have to push it very hard to get, so the forcing's up this way, and the displacement is something like a change in temperature, say because of CO2, or a change in land cover because of rainfall, something like that. If you have a less stable equilibrium, you move the system further for the same amount of input, the same amount of energy, maybe the same amount of CO2 or the same amount of rainfall. And what you really want to know when you're doing predictions, and I think this is true of landscapes as much as it is for climate, except for landscapes we might be interested in the sensitivity to policy, is whether you're in this sort of world or that sort of world. And of course, if you have a ball in a well kind of model, it's pretty clear that if you just gave it a random forcing, the way it responded to that forcing would reveal the shape of this well. And pretty much everything I'm going to say is about that idea. So if you have a very stable system, it will respond a small amount when you force it, and it will have short and fast fluctuations, because basically it can't get out of the well. If it's a much less stable equilibrium, responds a lot to forcing, it'll have larger and slower fluctuations. And actually everything I'm going to talk about is what you can get by looking at the difference between that and that across models. So, second conclusion, variability sensitivity connections are the basis for a number of what's already been described emergent constraints used to reduce uncertainty in climate projections. They're not yet used in landscape decision models. The question we have, and that Felix already raised, is whether they might be. Whether the models actually have sufficient stochasticity and nonlinearity, I'm not sure yet. But the stochasticity is fairly straightforward. You can just put noise on your forcing. So what are emergent constraints? This is my definition, but I think it's generally a kind of accepted one. They use an ensemble of models, so many different representations of a system, to identify relations between things you can measure. Variations might be seasonal cycle, might be variation from one year to the next, and future sensitivity. Okay, and they become a constraint because if you've got this relationship and you can measure the variations because they're observed, you obviously can, then you can constrain what your future looks like. So it's basically using that relationship between noise and sensitivity to your benefit. And this is a paper that came out from Femke Neisser last week in Nature Climate Change that Chris Huntingford and I were involved in. Very simple. As someone has already said, climate models are arguably the most complicated models we use in many locations around the world. They do disagree a lot though. They agree the world's warming, they agree it's going to warm enough to be a problem. They don't agree whether it's going to be 2 or 4 degrees. In fact, they don't agree by a factor of 3 in the long-term global warming to a given scenario. But if you look at these models, and we define this quantity ECS, which is equilibrium climate sensitivity, how much the globe warms on average when you double CO2, there's a range from 1.5 to 4.5. And if you then look at these complex models at how they vary in control simulations, these are ones where we don't increase CO2, we just let the model vary naturally, internal variability. You find models that are high sensitivity models. So ECS greater than 3 Kelvin here means doubling CO2 makes climate change increase by 3K, the climate warm by 3K. They're much broader. So you can already see this in these complex models, that if I've got a more sensitive model, high ECS, it will have more variations even if I'm not forcing it. And that's like that idea, that stupidly simple idea of a ball in a well really. It's consistent with that. Furthermore, what we often find is that this spread for a given model, which is shown here, this is basically the standard deviation of the decadal trend. If you just draw a line for every 10 years, calculate the trend and then look at the standard deviation of that, that's some measure of variability, is approximately linear in this thing we want to know. And that in a sense is like a fluctuation dissipation theorem. It says the fluctuations of this system, which are totally natural in this case, they're internally generated, are related to its sensitivity to external forcing. And that in itself would be, well, of great intellectual interest to me, but not very useful, except that often you can measure this thing. Right, so the idea of an emergent constraint is if you've got a relationship like this across models, there's a huge range of ECS, you see here, they go from 2 to about 5, and I can measure something here, I can get a constrained estimate of the thing I want to know. That's the basic idea. And I'm going to give you one from a bit closer to the issues we're talking about today, which is about the carbon sink in Amazonia. And this is something that is very uncertain across models. So I'm just going to unpack this a bit more. So it's an emergent constraint on the carbon loss from tropical land due to climate change. And it comes from just looking at the interannual variation in the CO2 growth rate. Right, so if you take the Mauna record, you'll see it go up because of anthropogenic emissions. If you detrend it, you'll see there's a variation in the growth rate that's quite significant. Turns out to be related to ENSO variability, to El Nino events. And we can use that as a constraint on this relationship across models I'm going to show you. Here's the unknown. Now, notice this in this generation of models, they all release carbon from the tropics if you warm the tropics up. So 1 Kelvin increase here leads to gigatons increase in the Hadley Center model that I was involved in developing of over 100 gigatons. But there's a range of these things going down to 30 or something. Some of these numbers are so small that compared to, say, the rate of current deforestation in Brazil that's just picked up, they're not worth worrying about, but some of them are really large and really undermine your ability to stabilize the system. So the question is, how can we know which of these is correct? And again, emerging constraints come to the rescue. So let's look at this. This is just observations now. This is how the CO2 content of the atmosphere is going up year on year. So we generally don't see the rate of increase, we just see the long-term change. And it's very spiky. Much more spiky actually than the emissions could account for. The human realm in this case, not always the case, is relatively slow to change compared to the land carbon sink. And if we detrend this thing actually, so detrend this thing, do a linear detrend or something, and look at the anomalies about the long-term trend, you've basically got a sort of variability of the carbon sink. And that variability, which is shown in black here, so for example in big El Nino events you tend to get carbon released from the tropics, and La Nina events you get uptake. That's correlated quite well with the tropical temperature anomaly. That's basically because when El Nino happens, it's hot in the tropics, respiration goes up, maybe fires increase and carbon's released. When a La Nina happens, the opposite's true. And we can do exactly the same as this for models because they're calculating this thing and this thing. So we can calculate a correlation between the CO2 growth rate anomaly, say at more or lower, and the temperature anomaly across models. So this is the thing we want to know. This is the thing that we can actually measure, and you can see the correlation yourself. This is a bit of a fluke if you think about it, because look at the dimensions of this. This is gigatons per year per Kelvin. The other one's gigatons per Kelvin. So what this implies, and we got really lucky here, but we published before we realised we were really lucky, is that there is a common timescale, a turnover timescale across all these models that might or might not be true. I think it's probably is roughly true, but you know, there's always this possibility that you're not going to get that. So now you've got an issue that you'd like to know that. It's very correlated with this thing. And the nice thing about this thing is you can actually measure it. And there's the measurement, because I just showed you the observational record here. So you immediately can say which models look realistic and which don't. And regrettably, mine doesn't. Okay, and there's therefore a line. This is called an emergent relationship, sensitive to the CO2 growth rate that we can measure against the climate loss from the tropics due to warming. And we can put other models on here too. And there's an observational constraint. And therefore, although my statistics colleagues will tell me this can be done properly and not the way I did it, you can sort of see by R you're going to get something like -50, not -200, not 0, around about -50. The beauty of this is it's the only time I've ever seen, well, the things like this, the only time I've ever seen where an ensemble of models tell you something more than you thought you knew from one. So when we all run our models, as Paula said, and we believe in our models, Peter may have said that we believe in a bit too much, we imagine that's pretty close to the truth because it's our model. And then we have a load of other models and they kind of destroy our belief in the power of model building. Then you compare them across the board, you basically just say, we know much less than we thought. We've got more models, it's worse than we thought. But this is the opposite. It basically says use the range to reduce the uncertainty. Okay, so that's one thing that is my argument for why we should embrace the noise in our systems. If it's not in our model systems, we ought to put it in, because it will reveal things like changing resilience. Another thing is the possibility that the sensitivity of your system is changing through time. And essentially you can get to a point where that well gets so flat that I showed you that the system's unstable, and that's what we call a tipping point, really. In the climate system, we're obsessed with these things. This is from my colleague Tim Lenton. These are all possible tipping points. Some of them have been seen in the paleoclimate record. Some of them have been seen in model simulations. So this is essentially the Amazon dieback that we just constrained, actually. But the thing is that they all have a transition from one state to another that's faster than the change in the forcing. And we're obsessed with them in the climate system. I think they're probably fairly rare in the climate system. But my suspicion is they're absolutely all over the socioeconomic system. That's my suspicion. Okay, so let me see if I can play. This is from my colleague Paul Ritchie. So there's a movie here. This is what's called a fold bifurcation. So this is relevant to something like the thermohaline circulation collapsing, you know, like in The Day After Tomorrow, that film, except not quite so fast as that. So this would be something like the freshwater input to the North Atlantic. This is the on state up here, so the +1 type state. This is the on state. And in a certain range of this freshwater input, or change in freshwater input, you've got 3 equilibrium states. This one, which is on, this one's largely off, and one in the middle that's unstable. So this state actually separates this basin of traction from that one. I'm just going to show you a movie, because it's just to show you that there's a common theme that links together emerging constraints and tipping point precursors. See if this will play. Oh, sorry. How do I play that then? Hello? Might need some help here.
Touch the screen.
Oh, it's actually touched the screen, is it? Maybe a bit better than that. Oh yeah, there we go. So all this has got noise. It's got noise applied to this very simple system. And you'll see, as the well's changing here, this becomes gradually more unstable and flips to the other state, and that's basically going into the off mode. Okay, here it goes into the off mode and sticks into this new potential well. So in that case, that sort of bifurcation, you basically have a potential landscape that's changing through time with regards to a time-varying input, in this case PT, which you can think of in the case of thermohaline circulation as freshwater input into the North Atlantic, for example. And this sort of fold bifurcation is seen a lot in systems, even in high-dimensional systems. So you might argue this is a ridiculously low-dimensional model to think about in the context of climate. It works quite well even for very high-dimensional climate models, because it turns out when you go through a tipping point, there's almost like a reduction in dimensionality of the system. There's a coherence to it that means very high-dimensional, very noisy kind of outputs become much lower dimensional. Okay. Right, so climate variability, changing variability may also reveal changes in system resilience. So even if that system didn't tip, if it got flat of the well, we'd get a change in variability. And so looking at variability is kind of a key, because it's a continual test of the resilience of your system. Right, so essentially, to go back to this picture, when we use emergent constraints, we look at the difference between that and that in different models to try and work out what a time invariant thing like climate sensitivity might be. When we're looking at tipping points in a given system, we're looking at how in time something might move from that stable state to that less stable state, and you extrapolate it and you go, hold on a minute, that's about to go unstable. And in these systems going through fold bifurcations, that's unbelievably effective actually. Even in paleoclimate records, you can kind of hindcast, if you like, where the instability might have occurred, say a glacial instability. Right. Okay, so here's another one. This is early warning signals. So this is that idea that the well's getting shallower. So as you approach the tipping point that we'll see in a minute, the time scale of the fluctuations, the time they take to relax back goes up, so the autocorrelation goes up and the variance goes up. So if you see these signals in your system, it's becoming less resilient and it might be on its way to a tipping point. Okay, and you can see here that at this point where it tipped, we'd already got quite a good record that said the variability of this system's going up, it's becoming less resilient. Okay, this is called critical slowing down, and you see it in lots of systems actually, not just fold bifurcations. Stochastic faulting is absolutely critical to this, and I actually think that we, in climate science, we've got models that develop internal variability, but I've also seen examples where you don't even need that sort of complexity. You don't need a kind of chaotic system for this to be done. For example, if we're driving a landscape model by aspects of broader economic development or GDP, I think we should be putting noise on it, because we won't otherwise see what the system might do. We won't otherwise detect whether its resilience is changing. It's not a difficult thing to do. Right, here's an example of what's called noise-induced tipping. So in this case, you've got two wells that are not changing. The variability of the system, the forcing of the system is sufficiently random, you hop from one to the other. And these are called danske events. They're basically rapid warmings and coolings in Greenland, shown by this proxy here. And I'm now going to show another animation, if I can actually do it, of Paul. Is it my finger? Do you think I've got a really terrible finger? Don't answer that. Yeah, it's coming out. So how do I start this? Have you got the special finger? Oh, there we go. Sorry. I've just stopped it. Okay, so this is a system where there's just two wells, but there's a lot of noise, so it just fluctuates from one to the other, essentially based on the size of the perturbation. If the perturbation is big enough. Now, if we didn't have noise in this system, you'd just see it stay in whichever state it happened to start in. You'd miss all the dynamics. So the noise actually reveals a total different, you sample this potential landscape much more. So I think noise is absolutely fundamental to understanding what a system's capable of, and how, most importantly, how you might change it. I'll come to that in a minute. So stochastic forcing changes the system's dynamics fundamentally in this case. And if we didn't have noise, we wouldn't even know there was a second well actually in this case. You just wouldn't know it. Right. Now, we basically think tipping points are really terrible, right? I mean, climate science is is based on this idea that you avoid dangerous change, and dangerous change is defined by tipping points, and you don't want any of them. But you think about how we avoid dangerous change. We need a transformational change in society, and that's a deliberate tipping point. We might not want to call it that, but it's a deliberate tipping point. It is an attempt to change the state of the system, not slowly because we haven't got enough time, but actually abruptly. And I really like this book. This is a popular science book many of you may have seen by Malcolm Gladwell, The Tipping Point, where there's all sorts of things in here, but it's from a economic, social point of view. So there's examples in here like I think it was Giuliani in New York getting rid of graffiti by just making sure it was painted over so fast so there was no positive feedback on people doing graffiti. It's also got a slightly less a less obviously social thing, which is the sale of hush puppies. I don't know if you've seen this one, where there's basically a tipping point here, and you can see where the feedback goes. Essentially, the way he argues, Gladwell, is that they were incredibly uncool. They were so uncool that cool people started to wear them, and cool people affect everyone else, and it took off. Yep, 5 minutes, okay. So they're often viewed more positively in social science than they are in natural science, and I think they're more prevalent actually. We just don't see them because we don't look at the world that way. And maybe we need a tipping point to get onto a pathway to sustainability. So here's the 1.5 degree target, the Paris target, and this is where the UK says it's going to get locally, which is to neutrality by here. The green line here is where we are. It's great when you see these pictures. They always turn over about 5 years' time. In this one, there's even actually a discontinuity between the lines. So there is a transformation required. And essentially, this is not the same pathway. When it's plotted like this, you're basically change the world abruptly. And I think we have to accept that these targets that are being set now do not require a gentle bending of the curve. They require non-linearity to be used. And we haven't discussed this, although if we do have another meeting at the Newton Institute, I'd love this to be a part of it. So these sort of dynamical system models are more obviously applicable to continuous systems like the differential equations that underlie, say, the thermohaline circulation. Probably true that networks are more appropriate for many of the things we worry about in the social realm, you know, whether it's public opinion or decision making. And in those networks, you often find really abrupt transitions as a function of connectivity. So you would expect, and you do see these sort of precursors of change in the system. My final argument is we're going to need to do this, or someone, not we, actually we're not going to do it, but we're going to need to, it's going to need to be used, this sort of transition. We can see it happening sometimes by chance, quite often mostly by chance. Think about public opinion about climate emergency, and maybe somewhere here is Attenborough, and so maybe somewhere here is Greta, and maybe there is a huge change in public opinion that, at least for a while, changes the state of the system, even changes the newspaper's view on it. Okay, so non-linearities and tipping points, for example, in social networks, may be needed to achieve a transformational change to environmental sustainability. Right, and I'm just going to try this one last movie. So this is I'm calling this a mathematical parable. This is what's called a pitchfork bifurcation. You come to some point here where the current state ends and you get two others, right? It's a very simple state. And there's a third state in the middle that's unstable. Now if we just ran this without any external forcing, just random variability, half the time it would go here, half the time it would go there, a bit like a coin toss really. And now I'm going to struggle for ages to get the movie to go. So we might imagine, for example, this is a single equilibrium, multiple equilibria. This could be changing global energy consumption. Maybe at this point we run out of energy, we have an energy crisis, and there's conditions on which way you go. And maybe this is changing carbon efficiency, so how much energy you get per unit carbon. You could then go to renewables or unconventional hydrocarbons. If you went this way, the carbon efficiency would go down, we'd be more carbon intensive, and if you went that way, we'd be less carbon intensive and more carbon efficient. Okay, so the trick then is, can you use the fact that when the system is here, it's very stable, it's very sensitive to inputs. So if you knew that, you would say, right, this is the time for my policy. It doesn't have to be a big policy. It can be quite a small policy. It just clicks the system to one state or the other. Right, so in this parable, what we're going to do is we're going to run the system, and in the second case of this, we're going to look at this autocorrelation, and when it gets to close to 1, we're going to say, this system's unstable, let's give it a flick. And that flick might be incentive, it might be regulation, it might be getting David Attenborough to say something on BBC, who knows what it might be. But we're going to change the state of the system and choose our final state. Sounding a bit like I'm power crazed here, I must admit. It's just that we can't actually run the damn thing. Here we go. So this is the case where we don't. It's the case where we don't do anything, and it doesn't do anything, right? And there's noise in the system, and in this case, it's going to go into the unsustainable world down here. Okay. And you'll see the autocorrelation does indeed go up as you get towards the instability. The red line here defines where we're going to impose our external forcing. So basically, when it gets unstable, we're going to go kick, 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 and that's what this purple thing is. And you can get yourself into the other state. Now, this is nothing like a serious model, right? But it just shows the point. If I'd applied that noise back here, it would not have been enough to change the state of the system. There was no other state to go to. The best time to apply it was when it was unstable, or getting unstable, when you knew there was another state to go to. Right, nearly done. Oh, maybe I'm not. Okay, so to come back to my rather bold initial question, is it better for a system to be sensitive or insensitive to policy inputs? You can think of it as policy optimism versus policy pessimism. If you're optimistic, you'd say policymakers have ultimate power. They want what they do to make a difference. They need to do it when it's sensitive. The problem with that is it's also a point where all your uncertainties are biggest. If you're a policy pessimist, you might say, well, policymakers can't do what they like. They've got all sorts of externalities like changes in the environment, Brexit, Trump, Boris, us. And you might say, I want, and Peter mentioned this, I want a pathway that's really resilient to those things I can't control. So which is best? Well, if you take that mathematical parable, you need them both. Right, you basically need this when you want to make the change. You need to know that your policy input will make a difference. And then once it's on the right path, you want nobody to be able to stop it. And so you do actually want it to be resilient. And that's what this happens in this system, is once the well gets deeper again, you're in a situation where perturbation don't matter so much. Okay, so final point. I think we need to recognise and use nonlinearity in our models, not hide from it, not try to imagine it's not there, in fact hope it is there. And I think we need stochastic forcing of models even when we might not imagine it's naturally internally generated. And my question therefore is, are landscape decision models sufficiently nonlinear and stochastic for us to do this sort of thing? And could we make them stochastic, maybe by just the forcing we put in, to see what their regimes might look like and whether there's things we might see that are interesting and useful. Okay, thank you.
We've got time for one very quick question.
Yeah, I was really interested in that last example. I think it's a really nice little toy model. It implies two things to me. First thing is that the best time to give it a kick is just before the instability.
Yep.
But you need to be able, for a policy, you need to be able to give it a kick with enough time for it to actually have an impact.
Yes.
You have to very carefully identify that period of time.
Yeah.
It's hard to persuade politicians to wait and wait and wait and wait.
Yeah.
And the second thing is there's a period immediately after the kick when you start down one branch, but the two branches are still pretty close to each other, and stochastic noise could flick you into the wrong branch even then.
Yeah.
So your kick still has to be large enough, ideally over large, to kick you so that your stochastic noise isn't going to flick you.
Very, very good points. And I think Rob Bradburn, who's not here, but I've spoken to about this because we've buddied up through DEFRA, uses the term tip and freeze. So this is this idea that actually you don't get to choose which state it goes to. It just goes to another state. You know, like Attenborough says something, or Greta says something, or Extinction Rebellion spins up, and then you freeze it in with a policy. So it's a bit more like making it a social norm by saying there's now a policy. And I think this happened with the smoking ban, actually. You know, if you'd done that 5 years earlier, no one would have taken any notice of it. It was the right time, and maybe it was already beginning to happen locally, and then policy can go, bang, right now, this is a new social norm. So oftentimes, I think this is really about an opportunism, looking at the system in terms of its stochastic variations and its nonlinearity, to go, right, this is the time, it's in the right state, bang, right, let's freeze it in. Maybe it's more like that. Okay?
Okay, cool. Come on, Dave.
So just the
Region
putting
16.
stochasticity into the models. That's exactly what we agree with you as well. There's one of the things in model discrepancies. You try to noise up some of the forces.
Right.
To capture this idea that you're not just on one path.
Yeah.
So that would be a really nice outcome from this idea. We're just talking different languages, so we never.
Yeah. Well, that's great. I think generally that seems to work well with putting noise in models that haven't got enough. Even in climate models, as you know, and weather forecast models, you put in stochastic parameterization. It makes the forecast better.
Yeah.
Cool. Thank you.
Okay, thanks.